These are 12 of the darkest places and darkest chapters scientists have ever found in the history of the universe, and every single one of them breaks a rule we thought space had to follow. One is a hole in the sky so big it took astronomers 16 years just to prove it wasn't completely empty. Another is a planet blacker than coal, orbiting so close to its star that it should be glowing, not vanishing. One is a black hole so massive it was mistaken, for 6 full years, for an ordinary faint star. Another is close enough to reach in a matter of years at the speed of light, yet stayed completely undetected until 2014. There's even a chance, and we mean this literally, that you are reading this from inside one of these dark places right now. If you're new here, stick around, because by the end of this you'll never look at a clear night sky the same way again. And if you want more deep dives into the universe's strangest corners, go ahead and hit subscribe now so you don't miss the next one. Let's start with the discovery that started it all, back in 1981, and the strange method astronomers use to find something by noticing it isn't there. Why is space even dark in the first place? Before we get into any of the 11 specific dark places on this list, it's worth asking a much bigger question first. One so basic it sounds almost silly to say out loud. Why is the night sky dark at all? Think about it for a second. The observable universe contains something like 100 to 200 billion galaxies, and the Milky Way alone holds somewhere between 100 and 400 billion stars. If the universe is infinite, or even just old enough and dense enough with stars, then every single line of sight you could possibly draw from where you're standing should eventually hit the surface of a star, somewhere out there in the distance. Picture standing in the middle of an endless forest. No matter which direction you look, your eye eventually lands on a tree trunk, because the forest simply never runs out. If stars were distributed the same way through infinite space, then every patch of night sky, no exceptions, should be packed edge to edge with starlight, and the entire sky should glow as brightly as the surface of the sun itself. Instead, when you look up, you mostly see black, with a few scattered points of light. That contradiction has a name, Olbers paradox, credited to the German astronomer Heinrich Wilhelm Olbers, who wrote about it in an 1823 paper. Olbers wasn't actually the first to notice the problem. The question can be traced back at least to the astronomer Johannes Kepler in 1610, and it was independently discussed by others in between, including the 16th century English astronomer Thomas Diggers. But it's Olbers' name that stuck to the puzzle, and it's a puzzle that genuinely stumped serious scientists for well over a century. Olbers himself proposed that distant starlight might simply be absorbed by dust floating in space, but the English astronomer John Herschel later pointed out a fatal flaw in that idea. Anything capable of absorbing that much starlight across the entire universe over billions of years would eventually heat up so much that it would start glowing brightly itself, which just relocates the problem instead of solving it. The real answer, once cosmologists finally worked it out, turned out to reveal something fundamental about the nature of the universe itself. The night sky is dark for a combination of two connected reasons. First, the universe is not infinitely old. It's roughly 13.8 billion years old, and light travels at a fixed, finite speed. That means we can only ever see light from objects close enough that their light has actually had time to reach us since the universe began. Stars and galaxies sitting beyond that boundary, no matter how many of them exist, are effectively invisible to us, not because they aren't there, but because their light simply hasn't arrived yet, and in some cases, thanks to the universe's ongoing expansion, never will. Second, the universe is expanding, and that expansion stretches the light from distant, receding galaxies toward longer, redder wavelengths. The exact same redshift effect that let Robert Kirshner map the Bootes void back in 1981. Push that stretching far enough, and light that started out as visible starlight gets shifted clear out of the range human eyes can detect, fading from view, even though the source itself is technically still shining. So the darkness of the night sky isn't emptiness in the way it might first appear. It's really a kind of horizon, a boundary drawn by the age of the universe and the speed of light working together. Every dark patch of sky you've ever looked up at is dark, partly because it's genuinely underpopulated with galaxies nearby, and partly because the universe simply hasn't existed long enough, or stayed static long enough, for every possible point of light to have reached your eyes yet. There's something almost humbling in that idea, once it sinks in. The darkness overhead, on any given night, isn't a void in the sense of nothing being out there. It's a kind of horizon of time itself, a boundary past which light simply hasn't had the chance to arrive, made visible not as a wall or an edge, but as an absence, stretched across the entire dome of the sky above you, every single night of your life. In a strange way, the entire premise of this video, the idea that there are specific, extra dark places worth singling out against an already mostly dark backdrop, only makes sense because the whole sky is already fighting a losing battle against true, infinite brightness. We're not looking for the dark spots in a bright universe. We're looking for the darkest spots in a universe that is, by its very nature, already mostly dark, and asking what makes some patches of that darkness stranger, colder, emptier, or denser than all the rest. With that bigger question settled, let's get into the specific places, starting with the discovery that, in 1981, first proved a hole in that darkness could be even emptier than the space surrounding it. How you find something that isn't there. Before we get to the void itself, it helps to understand the tool that found it, because the method is almost as strange as the discovery. Astronomers can't just point a telescope at the sky and see distance the way you'd see it looking down a hallway. Space doesn't come pre-labeled with mile markers, and there's no odometer ticking away as light crosses billions of years of empty vacuum. Instead, they rely on something called redshift, and the idea behind it comes from a property of light that most people only ever notice with sound. You've probably heard an ambulance siren change pitch as it passes you, dropping lower the moment it goes from approaching to moving away. That's called the Doppler effect, and light does something similar. As the universe expands, galaxies are carried farther apart from each other, and the light traveling from a distant galaxy toward Earth gets stretched out along the way, shifted toward the red end of the spectrum, the same way a departing siren gets stretched into a lower pitch. The farther away a galaxy is, generally speaking, the faster it's moving away from us, and the more its light gets stretched, meaning redshift becomes a kind of cosmic ruler. Measure the shift, and you can estimate the distance, without ever needing to physically travel there or bounce a signal off it and wait for an echo. In 1981, astronomer Robert Kirshner and a team at the University of Michigan were using exactly this technique, measuring redshifts for galaxy after galaxy, essentially building a three-dimensional map of the universe one data point at a time. It was slow, painstaking work, the kind of research that doesn't make headlines while it's happening, just years of pointing instruments at faint smudges of light and recording numbers, night after night, galaxy after galaxy, cataloging measurements that on their own told you almost nothing, and only became meaningful once enough of them had accumulated to reveal a pattern. Galaxy by galaxy, the map was slowly filling in, the way a puzzle does when you've placed enough pieces to start seeing the picture. And then, about 700 million light-years from Earth, the picture just stopped. Where there should have been galaxies scattered across the map like sand on a beach, there was almost nothing. Kirshner's team published a paper with a title that undersells the discovery by a mile: a million cubic megaparsec void in Bootes. That question mark at the end says everything about how strange this was. Nobody expected to find a hole this big, and at first, nobody was even sure they believed it themselves. Finding a void isn't like finding a planet or a star, where you're looking for a bright dot against a dark background. It's the reverse. You're looking for an absence, a gap in a pattern that's supposed to be roughly the same everywhere you check it. You only notice it because of what's missing, and proving something is genuinely missing, rather than just unobserved, or hiding behind foreground dust, or simply too faint for the equipment of the day, takes years of careful, repeated measurement. That region came to be called the Bootes Void, named for the constellation it sits in the direction of. But it picked up a nickname almost immediately that stuck far better: the Great Nothing. And the numbers behind that nickname are what make it worth talking about more than 40 years later. The void stretches somewhere between 250 and 330 million light-years across, depending on which measurement you trust, which means the Milky Way galaxy could be dropped into it billions of times over and still have room to spare. To put it in perspective, that's somewhere around 1 to 2% of the entire diameter of the observable universe, contained in a single blank patch of sky, roughly centered near the star 38 Bootes. Here's where it gets genuinely eerie though. Based on how densely galaxies are packed in a typical, unremarkable region of space, roughly one galaxy for every 10 million light-years, NASA has estimated that a space this size should contain something like 2,000 galaxies. Astronomers went looking, and by 1997, after 16 years of searching, they had found exactly 60 galaxies where 2,000 should be. That's not empty, not technically, but it's close enough to earn the name. And the void being real, being confirmed and reconfirmed over decades of follow-up observation, ruled out a couple of the wilder explanations people might jump to. It's not a black hole, because black holes don't leave room for 60 galaxies to exist quietly inside them. It's not a dark nebula either, the kind of dust cloud that just blocks our view of what's actually there, because comparisons with known dark nebulae showed the physics simply doesn't match. This is a real region of space with a genuinely reduced amount of matter in it, sitting there since long before humans built the telescopes capable of noticing it. One astronomer connected to the discovery put the strangeness of it into a single sentence that's worth sitting with. If the Milky Way had happened to form in the center of the Boötes void instead of where it actually is, we wouldn't have known other galaxies existed until the 1960s. Our entire understanding of the universe beyond our own galaxy, the discovery that spiral nebulae were actually separate island galaxies, the entire field of extragalactic astronomy, all of it would have been delayed by decades, simply because of where in space we happened to be born. Every major cosmological breakthrough of the 20th century assumed a night sky full of visible neighbors, stripped most of those neighbors away, and the whole timeline of human self-understanding shifts along with it. And that idea, that our location in the universe shapes what we're even capable of discovering, turns out to be a lot more relevant to us than you might think. Because as we're about to get into, there's mounting evidence that we might already be living somewhere similar. It's worth knowing that astronomers don't treat every underdense region of space as the same kind of object. Researchers studying these structures have generally sorted them by scale into rough categories: small voids, up to about 100 megaparsecs, or roughly 325 million light-years, across; large voids, spanning somewhere between 100 and 1,000 megaparsecs; and giant voids, larger still. Both the Boötes void we just covered and the KBC void we're about to get into sit up near the boundary between the large and giant categories, among the biggest individual structures ever proposed in the observable universe, which is part of why either one, on its own, would already be remarkable. This kind of classification isn't just bookkeeping either. The scale of a void determines what physical process could plausibly explain it, since the mechanisms capable of clearing matter out of a region a few 100 million light-years across are not necessarily the same mechanisms capable of doing so across a region several times that size. The fact that there may be two such enormous structures, one confirmed since 1981 and one still being actively debated, both worth discussing in the very same conversation about our own cosmic neighborhood, says something about just how lumpy and unevenly distributed matter really is at the largest scales anyone has ever measured. We might already live in one of these. Here's a thought that tends to sit uneasily once you actually process it. Growing evidence suggests the Milky Way itself might be sitting inside a giant cosmic void, not as an outside observer studying one from a safe distance, but as a resident. It's called the KBC void, named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who published the key research describing it in 2013, and it also goes by the simpler name, the local hole. Estimates of its size vary depending on the study, but the most commonly cited figure describes a roughly spherical underdensity stretching close to 2 billion light-years across, with a radius of around 1 billion light-years, making it, by some measurements, the largest void ever proposed, larger even than the Boötes void we just covered. Some researchers have also described a smaller, closer region called the local void, roughly 200 million light-years across, which may itself sit inside the larger KBC structure, a hole within a hole, if the model holds up. The evidence isn't limited to one method or one wavelength of light either, which is part of what makes it compelling. Multiple independent surveys, working across optical light, infrared, X-ray, and radio wavelengths, have all pointed toward the same basic conclusion. The region of space immediately around us contains noticeably less matter than average. Researchers have used everything from the 2-mass redshift survey, which catalogued more than 43,000 galaxies within 380 million light-years of Earth, to surveys of X-ray emitting galaxy clusters, to studies of the cosmic radio dipole, a subtle directional signal detected across the entire sky. Estimates of exactly how much less matter is out there vary a fair amount depending on the study and the distance scale being measured, with figures ranging anywhere from about 15 to 50% below the cosmic average, though a commonly cited working figure lands around 20 to 30% underdense within roughly a billion light-years of us. One specific analysis put the contrast even higher, describing a density roughly 46% below average between about 40 and 300 megaparsecs from the local group. To be completely fair to the science here, this is genuinely disputed territory, not a settled fact. Some research teams have found evidence against the void's existence at the scale originally proposed, arguing the claimed underdensity doesn't hold up once you look beyond its supposed radius. Other researchers have pushed back on those objections in turn, pointing out weaknesses in that counter-analysis and keeping the debate active. Newer work presented in 2025 using baryon acoustic oscillation data, a completely different method of measuring the large-scale structure of the universe, reportedly found a void model to be around 100 million times more statistically likely than a universe without one in that particular dataset. This is what real, ongoing cosmology looks like, not a single clean answer, but competing analyses of the same messy universe, refereed one paper, one survey, one dataset at a time. What makes the KBC void more than just a curiosity, though, is what it might explain. For years, cosmologists have been wrestling with something called the Hubble tension, a stubborn disagreement between two different ways of measuring how fast the universe is expanding. Measurements based on the nearby universe, using exploding stars called supernovae and pulsating stars called Cepheid variables, consistently produce a higher expansion rate, commonly cited around 73 kilometers per second per megaparsec, than measurements based on the cosmic microwave background, the ancient light left over from the early universe, which tend to produce a noticeably lower figure. Both measurements have been checked and rechecked for years, refined with better instruments and larger samples, and the gap between them refuses to close, which has left physicists hunting for something, anything, that might explain the discrepancy without breaking the rest of known physics. It's a strange, almost uncomfortable situation for a field that generally prides itself on precision. Two entirely different, entirely well-established methods, each independently checked by multiple research teams, simply refuse to agree with each other, and nobody has yet produced an explanation that satisfies everyone. A local void offers one possible answer. If the Milky Way sits inside a large region with less matter than its surroundings, the gravity in that region would be slightly weaker than average, and matter nearby would experience a gentle outward pull toward the denser regions surrounding the void, the same way water flows out of a low-pressure area, or the way a ball placed near the rim of a shallow bowl rolls toward the deeper, heavier edges. Astrophysicist Indranil Banik, who has studied this possibility in depth, put it directly. By now, it's pretty clear that we are in a significant underdensity. In one of his calculations, he found that a void of this size could locally boost the measured expansion rate by around 11%, which happens to be almost exactly the gap researchers have been trying to explain for years. Separately, researchers modeling this outflow using a modified theory of gravity found that it successfully predicted something called the bulk flow curve, an independent measurement of how galaxies in our region are drifting, which had already been observed but never fully explained. A rare case where a model built to solve one specific puzzle turned out, almost as a bonus, to also match a completely separate set of observations nobody had originally asked it to explain. Sit with that for a second. If this holds up, it would mean that one of the most persistent open puzzles in modern cosmology, a genuine crack in our understanding of how fast the entire universe is expanding, might be explained not by some exotic new form of energy or an error in our instruments, but simply by where we happen to be standing. We wouldn't be measuring the universe wrong. We'd be measuring it correctly, from inside a slightly emptier than average neighborhood, and mistaking our local conditions for a universal law, the cosmic equivalent of stepping on a bathroom scale, positioned on a slight downward slope, and wondering why your weight keeps coming out different from your friend's scale down the hall. The original 2013 study behind the discovery, led by Keenan, Barger, and Cowie, took a specific approach worth understanding. Rather than simply counting galaxies, which can be skewed by which galaxies happen to be bright enough to detect at a given distance, the team measured what's called the K-band luminosity density, essentially the total amount of infrared light being given off by galaxies at different distances from us. Infrared light is a good proxy for a galaxy's actual stellar mass, since it traces the light from a galaxy's cooler, longer-lived stars, rather than just its brightest, most short-lived ones. Measuring that luminosity density out to roughly 300 megaparsecs, the team found it rising steadily with distance, reaching values around 1.5 times higher than what's measured immediately around us, once you get out past a redshift of about 0.1. That steady rise, matched across multiple independent follow-up surveys using different telescopes and different wavelengths, is what convinced a growing number of researchers that the underdensity isn't a fluke of one particular dataset, but a genuine, repeatable feature of our corner of the universe. It's worth being clear that this remains an active area of research rather than a closed case, and not every cosmologist agrees on the size, depth, or even the reality of the KBC void as originally proposed. But the fact that it's even in serious contention as an explanation for one of astronomy's biggest unsolved mysteries tells you something important. We may not need to travel across 1 billion light-years of space to find one of the darkest, emptiest places in the universe. We may already be living in the middle of one, tracing its edges with the very telescopes built here. Inside it, on a small rocky planet, orbiting an ordinary star, sitting in a quieter-than-average patch of an already mostly empty universe. The ink-black patch you can see with your own eyes. Not every dark place in space needs a telescope to find. Long before Robert Kirshner's redshift survey, long before Europeans had even sailed far enough south to notice, people living in the southern hemisphere were already looking up at a strange black smudge sitting right next to one of the sky's most recognizable star patterns. Not every dark object needs to be big, or hot, or ancient to earn a place on this list. Some of them just need to be quiet enough and cold enough that even our best instruments took decades to finally notice them sitting there. That smudge is the Coalsack Nebula, and unlike the voids we've just covered, it isn't empty space at all. It's the opposite in a way. It's a dense cloud of interstellar gas and dust, thick enough to completely block the light of the stars behind it, which is exactly why it looks like someone reached up and erased a chunk of the Milky Way. It sits near the Southern Cross, in the constellation Crux, roughly 500 to 600 light-years from Earth, depending on which measurement you go with, and it spans about 5 degrees by 7 degrees across the sky, almost matching the size and shape of the cross-shaped constellation it sits beside, covering something like 26 square degrees in total. An area of sky many times larger than the full moon appears from Earth, all of it rendered essentially invisible, not because nothing is there, but because everything there is simply too dark and too close-packed to let any starlight through. The first European to write it down was the navigator Vicente Yáñez Pinzón, back in 1499. Amerigo Vespucci reportedly gave it a name a few years later, calling it Il Canopo Fosco, and it also picked up the nickname the Black Magellanic Cloud, a kind of dark twin to the two bright glowing satellite galaxies known as the Magellanic Clouds that sit nearby in the southern sky. The first formal scientific description came later still, from Peter Martyr, sometime between 1511 and 1521, and the French astronomer Nicolas Louis de Lacaille documented it again during his 1751 to 1752 survey expedition to South Africa. But here's the thing, none of those European names, and none of those formal descriptions, were the first names it ever had. Cultures across the southern hemisphere had been telling stories about that black patch for far longer, including the Basawa people of Botswana, who saw it as the head of a dark giraffe stretched across the stars, and other southern hemisphere traditions have folded it into their own constellations, built not from patterns of stars, but from patterns of darkness itself, reading shapes into the gaps in the Milky Way, the same way northern cultures read shapes into clusters of bright points. In that sense, the Coalsack may be one of the very first dark places ever consciously identified and named by any human culture on Earth, recognized and storied long before anyone had a word for nebula at all. What's actually blocking the light isn't a wall of solid matter, it's something closer to fog. The dust grains inside dark nebulae like the coal sack are believed to be coated in frozen water, nitrogen, carbon monoxide, and other simple organic molecules, and that coating is enough to absorb and scatter visible light almost completely. Starlight trying to pass through the coal sack gets dimmed by roughly 1 to 1.5 magnitudes, which might not sound dramatic until you remember that's enough to make entire fields of stars functionally disappear from view, replaced by what looks, to the naked eye, like a genuine hole in the Milky Way's glow. On a clear, dark night, away from city lights, that patch is one of the few objects in the sky you can identify purely by its absence, a black shape cut cleanly out of a field of stars. Most people who spend time observing it describe it as looking almost perfectly uniform, a flat, featureless black silhouette sitting against the mottled glow of the Milky Way's star fields. Only under exceptional conditions, no moonlight, no light pollution, no atmospheric haze, do careful observers start to make out subtle internal structure within it, faint filaments and texture hiding inside what looks, at first glance, like a single uninterrupted patch of nothing. And here's a detail that flips the whole story on its head. The coal sack isn't a graveyard, it's a nursery. Astronomers expect that portions of this dark, dust-choked cloud will eventually collapse under their own gravity and ignite into brand new stars, the same way coal itself can be burned for fuel, which is a strange kind of poetry for something named after coal in the first place. What looks like an absence of stars right now is, on a long enough timescale, a stockpile of raw material waiting to become stars later. Every dark nebula, like this one, is, in a sense, a paused sentence, matter gathered and cooling, and waiting for gravity to finally finish the thought, sometime long after every person who has ever looked up and noticed the coal sack is gone. The Southern Cross that the coal sack sits beside has become genuinely important to human culture too, appearing on the flags of Australia, Brazil, New Zealand, Papua New Guinea, and Samoa. And the European Southern Observatory even built the cross shape into its own logo. So this dark patch of sky has been sitting there next to one of the most culturally significant star groupings on Earth for as long as our species has been looking up, quietly reminding anyone who notices it that darkness in space isn't always empty. Sometimes it's just waiting, a quiet stretch of raw material with a lit fuse many thousands of years too long for anyone alive to watch it burn. It's worth pausing here for a second, because we've now covered two completely different kinds of darkness back to back, and the contrast matters. The boat is void and the KBC void are dark because there's almost nothing there. Vast stretches of space with far fewer galaxies than statistics say there should be. The coal sack is dark for the exact opposite reason. There's too much there, a wall of dust and gas so dense that light simply cannot get through it. Two objects, both described as dark, produced by mechanisms that are near total opposites of each other. That pattern is going to repeat throughout this list, and it's worth keeping in the back of your mind as we go. When someone tells you a place in space is dark, that single word can be hiding two completely different physical stories, an absence or an obstruction, and figuring out which one you're looking at is often the entire scientific puzzle, colder than the afterglow of creation itself. If the coal sack is dark because it's blocking light, the next place on this list is dark and cold, for reasons that are almost the opposite. This is a location where the leftover heat of the Big Bang itself, the faint background warmth that fills literally every corner of the universe, is actually warmer than the object we're about to describe. It's called the Boomerang Nebula, and it holds a very specific, very strange title, the coldest known natural place in the entire universe. It was first spotted in 1980 by astronomers Keith Taylor and Mike Scarrett, using the Anglo-Australian telescope at Siding Spring Observatory, and they named it for the faint curved shape they saw in its two lobes. Later, sharper images from the Hubble Space Telescope revealed the shape was more of a bow tie than a boomerang, but by then, the name had already stuck, the way early, slightly wrong first impressions of the universe so often do. The real headline came 15 years later. In 1995, astronomers Raghvendra Sahai and Lars Åke Neumann used the 15-meter Swedish ESO submillimeter telescope in Chile to measure the nebula's temperature directly, and what they found was almost hard to believe. The Boomerang Nebula sits at about -272 degrees Celsius, which converts to roughly -458 degrees Fahrenheit, or right around 1 Kelvin on the scale physicists actually use for temperatures this extreme. Absolute zero, the theoretical coldest possible temperature in existence, the point where matter runs completely out of heat energy to give up, is -273.15 degrees Celsius, or 0 Kelvin exactly. That means the Boomerang Nebula is sitting barely 1 degree above the absolute floor of the universe, colder than anything that occurs naturally anywhere else we've measured, and more than 3 times colder than the coldest naturally occurring temperature ever recorded on the surface of Earth. To understand how extreme that is, consider what the background temperature of the universe actually is. Every corner of space is bathed in leftover radiation from the Big Bang, called the cosmic microwave background, sitting at a steady -270.4 degrees Celsius. That's the ambient temperature of the cosmos itself, the warmth that fills the empty vacuum everywhere you look, even in the gaps between galaxies where nothing else exists. The Boomerang Nebula is colder than that. It's the only known natural object in the universe that has ever been measured to be cooler than the background radiation left behind by the birth of everything, meaning it actually absorbs a small amount of that ancient light rather than simply matching it, siphoning warmth from the universe itself instead of radiating any back. So how does something get colder than the universe's own baseline temperature? The answer is a kind of natural refrigeration. At the center of the Boomerang Nebula is a dying sun-like star that has been violently shedding its outer layers, expelling roughly 1,000th of a solar mass of material every year for about 1,500 years, a rate 10 to 100 times faster than similar dying stars nearby. That material blasts outward at speeds estimated around 500,000 kilometers per hour, and when gas expands that quickly and that violently, it cools. The exact same physics that makes the spray from an aerosol can feel cold on your skin, just scaled up to a stellar level of violence. Physicists sometimes describe this as adiabatic cooling. Expand a gas fast enough without letting it absorb heat from its surroundings, and its temperature has nowhere to go but down. The fastest, most extreme pockets of that outflow have been measured at just half a degree above absolute zero. Follow-up observations using the Atacama Large Millimeter Array, or ALMA, confirmed the extreme cold and mapped the nebula's true structure in far more detail than the original 1995 measurements could manage, revealing an hourglass-shaped inner nebula surrounded by a colder, roughly round outflow of gas, along with a compact source of dense material sitting right at the nebula's waist, likely a disk of large, millimeter-sized dust grains encircling the dying star. Researcher Raghvendra Sahai, who led much of this follow-up work at NASA's Jet Propulsion Laboratory, described the Boomerang Nebula's temperature record as cosmologically crisp, and noted that the object had actually been theoretically predicted before it was confirmed. He had calculated, based on the physics of dying stars losing mass at extreme rates, that a pre-planetary nebula with exactly the right conditions could plausibly cool below the temperature of the cosmic microwave background itself. And the Boomerang Nebula turned out to be almost a textbook example of that prediction playing out in real space, a rare case of the universe's darkest, coldest known corner being worked out on paper before it was ever actually measured. There's one more twist worth mentioning though. According to research from the National Radio Astronomy Observatory, parts of the Boomerang Nebula actually appear to be warming up as it ages, which means its reign as the coldest place in the known universe might not last forever. Even the record holder for coldest place in existence, it turns out, is not a permanent title. It's a temporary condition, brought on by one specific dying star going through one specific violent phase of its death. And someday, whether in 100 years or 10,000, the Boomerang Nebula will warm back up and hand the title to whatever object claims it next. For now, though, this dying star's violent last breath holds a record that most of the universe, including the empty vacuum of space itself, cannot claim. A fitting irony for an object born from a star in the process of ending. A planet darker than coal. Let's shift from a place that's cold to a place that's dark, in the most literal sense possible. a world that swallows almost every photon of light that touches it. Its name is TRES 2b, discovered in 2006 by a program called the Transatlantic Exoplanet Survey, which is where the name comes from. It's a gas giant roughly the size of Jupiter, orbiting a sun-like star called GSC 03549028111, somewhere around 700 to 750 light-years away in the constellation Draco. And on paper, it doesn't sound unusual. It's what astronomers call a hot Jupiter, a large gas planet locked into an extremely tight orbit around its star, circling its sun in just 2.5 days at a distance of roughly 3 million miles, heated to somewhere around 1,800 degrees Fahrenheit, hot enough to soften metal here on Earth. What makes it remarkable isn't its size or its heat, it's what happens to light when it hits the planet's surface. In 2011, using data from NASA's Kepler Space Telescope, astronomer David Kipping of the Harvard-Smithsonian Center for Astrophysics led a team that measured just how much sunlight TRES 2b actually reflects back into space. The number they landed on was less than 1%. Some of their models put the true reflectivity, technically called the geometric albedo, as low as 0.04%, an almost absurdly small number for an object the size of an entire planet, a figure so low it's easy to misread as a typo the first time you see it written down. For comparison, Jupiter itself, wrapped in bright, swirling clouds of ammonia, reflects more than 1/3 of the sunlight that hits it, which is why it's one of the brightest objects in our night sky, easily visible without a telescope on a clear night. TRES 2b reflects almost none of it. Kipping described the discovery in blunt terms. Being less reflective than coal, or even the blackest acrylic paint, this makes it by far the darkest planet ever discovered. He went further, describing what it might actually look like up close: a near-black ball of gas, with a slight glowing red tinge to it, a true exotic amongst exoplanets. That red tinge matters. TRES 2b isn't glowing because it's reflecting starlight. It's glowing because it's so hot that it's emitting its own faint light, the same basic physics that makes a stove burner glow dull red before it gets hot enough to turn white. Picture a planet the mass of 1.5 Jupiters, hanging in permanent orbital lockstep with its star, one face forever baked, radiating a low red light out into space instead of bouncing back the light that hits it. If you could somehow stand on a hypothetical moon nearby and watch it hang in the sky, it likely wouldn't look like a planet at all, in any conventional sense. It would look closer to a dim ember, a shape you could only make out because it was slightly darker and slightly redder than the black of space surrounding it. And here's the part that keeps this planet interesting more than a decade later. Nobody fully knows why it's this dark. Astronomers have floated a few possible explanations. One is that the planet's scorching proximity to its star simply prevents the kind of reflective, ammonia-based clouds that make Jupiter so bright from ever forming, since ammonia clouds need cooler temperatures to condense in the first place. Another is that its atmosphere might contain light-absorbing chemicals, like vaporized sodium, potassium, or gaseous titanium oxide, essentially exotic ingredients that soak up light instead of bouncing it back. Researchers have noted that this second explanation carries its own puzzle, since the same extreme heat that could vaporize those metals into the atmosphere in the first place is also what strips away the very clouds that would normally help a planet reflect light, meaning TRES 2b's darkness may not come from any single dominant cause, but from several separate effects of its extreme proximity to its star, all compounding on top of each other at once. But Kipping himself was honest about the limits of any explanation, saying, "It's a mystery as to what's causing it to be so dark. There's a good chance it's a chemical we haven't even thought of yet." The measurement itself was a technical feat worth pausing on too. By combining Kepler's precision with observations across more than 50 separate orbits of the planet, the team detected a brightness change of just 6 parts per million, at the time the smallest such signal ever picked up directly from an exoplanet. That's a measurement equivalent to noticing a single dim candle flicker from thousands of miles away, and it's what lets scientists separate the planet's own faint glow from the overwhelming light of its host star sitting right beside it, a star roughly 1 billion times brighter than the signal they were trying to isolate. It's worth understanding what hot Jupiter actually means as a category, because TRES 2b is far from the only planet like it. even if it's the darkest one found so far. When the first hot Jupiters were discovered in the 1990s, they genuinely upended what astronomers expected planetary systems to look like. In our own solar system, gas giants sit far out. Jupiter takes about 12 years just to complete one orbit around the Sun. A hot Jupiter, by contrast, is a similarly massive gas planet that somehow ended up parked shockingly close to its star, close enough to complete a full orbit in a matter of days rather than years. TRES 2b's 2.5-day orbit puts it firmly in that category, and being that close comes with a predictable side effect. Over time, the star's gravity locks the planet's rotation to its orbit, the same tidal mechanism that keeps the same side of our moon always facing Earth. That means one side of TRES 2b almost certainly faces its star permanently, baking under constant, direct starlight, while the other side faces away into permanent darkness, never receiving direct light at all. A planet with one face forever lit and one face forever in shadow, and even the lit side, the one constantly bombarded with starlight, still somehow manages to swallow nearly all of it, rather than shining back. So somewhere out in Draco, there's a planet the size of Jupiter, orbiting close enough to its star to be blasted with heat, and yet somehow managing to swallow almost every bit of light that reaches it, glowing faintly red, in a darkness that scientists still can't fully explain. It's a reminder that dark doesn't always mean cold or empty. Sometimes the darkest thing in a scene is standing directly in the spotlight, absorbing everything pointed at it and giving almost nothing back. A planet-sized void hiding in plain sight, right next to the very star that should be lighting it up. The first black hole humanity ever saw. For most of the history of astronomy, black holes were a mathematical prediction, not a photograph. The concept traces back to 1915 and 1916, when Albert Einstein published his general theory of relativity, and the German physicist Karl Schwarzschild, working on the topic within months while serving on the front lines of the First World War, found one of the very first exact solutions to Einstein's equations, a solution describing an object so dense that nothing, not even light, could escape its gravity past a certain boundary. For decades afterward, most physicists, reportedly including Einstein himself at times, treated this as a strange mathematical curiosity rather than something that could genuinely exist in nature, an elegant but purely theoretical edge case rather than an object anyone expected to actually find sitting somewhere in the sky. It took until the mid-20th century for the astrophysics community to widely accept that these objects weren't just equations on a page, and it was the physicist John Wheeler who, in the late 1960s, popularized the term that stuck: black hole. Once the idea was taken seriously, indirect evidence started accumulating quickly. First from the discovery of quasars in the early 1960s, extraordinarily bright, distant objects that seemed to demand an incredibly compact, incredibly massive engine at their core, and later, from decades of observing stars and gas swirling around invisible points of gravity at the centers of nearby galaxies, including our own. Einstein's equations suggested they should exist. Decades of indirect evidence, stars whipping around invisible companions, gas being torn apart and heated to enormous temperatures, all pointed towards something real and unimaginably dense sitting at the centers of galaxies. But nobody had ever actually pointed a telescope at one and gotten a picture back. That changed in April 2019. The object in question sits at the center of a massive galaxy called M87, located in the constellation Virgo, and its black hole, now formally designated M87, became the very first black hole in human history to be directly imaged. The picture itself, released by the Event Horizon Telescope collaboration on April 10, 2019, shows exactly what theory had predicted for decades: a glowing, slightly uneven ring of superheated material circling a perfectly dark, circular void at the center, the black hole's shadow, the point where light itself gets bent and swallowed by gravity too strong to escape. To understand how enormous a technical achievement this actually was, you have to understand the scale of the object being photographed. M87's mass is estimated at around 6.5 billion times the mass of our Sun, based on the motion of stars orbiting it, though earlier gas-based measurements had put the number at roughly half that, a discrepancy the EHT observations helped narrow down considerably. The ring of light captured in the image measures only about 42 microarcseconds across on the sky, an angle so small that EHT scientists have compared the achievement to being able to read the text on a coin sitting on the surface of the Moon, or to photographing an orange sitting on the surface of Mars from Earth. Try picturing that for a moment. An object 55 million light-years away, imaged with enough precision to make out fine structure across a target smaller, from our vantage point, than almost anything else humans have ever attempted to resolve. For comparison, even Hubble Space Telescope images, famous for their sharpness, typically resolve details thousands of times larger in angular terms than what the Event Horizon Telescope managed to pull off with M87. A difference achieved not through a single larger mirror, but through the sheer geographic spread of linking observatories separated by the width of an entire planet. No single telescope on the planet is remotely capable of that kind of resolution on its own. So the EHT collaboration built something unprecedented instead. They linked 7, later 8, radio observatories scattered across the globe, from Hawaii to Spain to the South Pole, into a single coordinated network using a technique called Very Long Baseline Interferometry. Every telescope in the network observed the same target at the exact same moment, and their combined data was later processed together, effectively turning planet Earth itself into one giant telescope, roughly the size of our world. Each site recorded torrents of raw data onto physical hard drives, so much data that some of it reportedly had to be shipped by airplane rather than transmitted over the internet, because it was faster to fly the drives to a central processing center than to send the files digitally. The image took years to produce, even after the observations were complete, requiring careful calibration and multiple independent imaging teams working somewhat separately from each other, specifically so their results could be compared and checked against one another before anyone trusted the final picture. The Event Horizon Telescope collaboration itself was, and remains, a genuinely massive undertaking, involving more than 200 researchers across dozens of institutions and countries, coordinating observatories on 4 different continents, all of whom needed to agree, independently, that the same faint ring of light was really there before the announcement could go public. EHT board member Paul T.P. Ho described the moment of confirmation this way. Once the team was confident they'd genuinely imaged the shadow, they compared their observations to extensive computer models built on the physics of warped space, superheated matter, and powerful magnetic fields, and found that many of the image's features matched theoretical predictions with startling accuracy. The image also confirmed something else. M87's black hole appears to be powering an enormous jet of material blasting outward from its vicinity, a jet so large that later observations found it stretching tens of millions of times farther across than the event horizon itself, a thread of superheated particles flung outward across a scale that dwarfs the black hole that launched it by an almost incomprehensible margin, visible enough in follow-up gamma-ray observations that researchers described witnessing dramatic flares from the jet years after the original image was released. For physicists, the image did more than confirm black holes were real. It offered a direct test of Einstein's century-old theory of general relativity under the most extreme gravitational conditions found anywhere in nature, and the theory held up. Every prediction, the size and shape of the shadow, the way light bent around the object's edge, matched what a century of mathematics said should happen. Scientists had been describing black holes in equations since long before any of the astronomers involved were even born. In April 2019, for the first time, the universe let them see one, and everything the mathematics had predicted about how darkness itself should look turned out to be exactly right. The invisible neighbor 7 light-years away. Every dark object covered so far has been distant, hundreds, millions, or billions of light-years from Earth. This next one breaks that pattern completely. It's practically next door, in cosmic terms, and it still managed to stay almost invisible. Its official name is WISE J 0855 1010.83-071442.5, which astronomers understandably shortened to WISE 0855, and it was discovered in 2014 by Kevin Luhman, an astronomer at Penn State University, using data from NASA's Wide Field Infrared Survey Explorer. It sits roughly 7.2 to 7.4 light-years from Earth, making it the fourth closest known star or star-like system to our Sun, closer than the vast majority of stars visible in the night sky. And yet it took until 2014, decades into the era of modern astronomy, for anyone to even notice it was there. WISE 0855 is what's called a brown dwarf, sometimes described as a failed star. It formed the same way a star does, through the gravitational collapse of a cloud of gas and dust, but it never gathered quite enough mass to ignite the nuclear fusion that makes true stars shine. Astronomers classify brown dwarfs by spectral type, broadly running from the warmer L and T dwarfs down to the coldest known category, Y dwarfs. And WISE 0855 sits among the coldest examples of that coldest class. A late Y dwarf by classification, cool enough that its light output is dominated almost entirely by leftover heat from its own formation, rather than any ongoing fusion process, slowly radiating away the energy it was born with, the way a dying ember cools long after the fire itself has gone out. With a mass estimated at somewhere between roughly 3 and 10 times that of Jupiter, depending on the study, and a size close to Jupiter's own radius, it sits in an odd middle ground, too large and too dense to be called a planet in any conventional sense, but never massive enough to become a genuine, burning star. What makes it worth including on this list is its temperature. Estimates have varied somewhat as measurement techniques improved, ranging from around 250 Kelvin in earlier studies up to roughly 285 Kelvin in more recent JWST observations. But even at the higher end, that works out to somewhere around -10 to -24 degrees Fahrenheit, making WISE 0855 the coldest brown dwarf ever discovered, and nearly as cold as Jupiter itself, which sits at around 130 Kelvin. For comparison, our Sun's surface temperature is just under 5,800 Kelvin, meaning WISE 0855 runs at less than 5% of the Sun's temperature, cold enough that astronomer Andrew Schemmer of UC Santa Cruz described it as the first object after Earth, Mars, Jupiter, and Saturn, likely cold enough to host actual water clouds in its atmosphere. In 2016, using the Gemini North Telescope in Hawaii, Schemmer's team found strong evidence that WISE 0855 does exactly that, the first clouds of water, or water ice, ever detected on any object outside our own solar system. We would expect an object that cold to have water clouds, and this is the best evidence that it does, Schemmer said at the time. Being this cold comes with a strange consequence. It's also nearly impossible to actually see, a genuine paradox for an object that also happens to be one of the closest things to Earth on this entire list. WISE 0855 emits almost none of its energy at visible wavelengths, radiating instead almost entirely in the mid-infrared, wavelengths of light completely invisible to the human eye, and even difficult for many telescopes to detect. Even the largest ground-based telescopes on Earth can only just barely make it out, and for years after its 2014 discovery, astronomers had only enough data to estimate rough properties, without being able to actually break its faint light down into a detailed spectrum the way you'd want to, in order to study its chemistry in any depth. Astronomer Kevin Luhman, who discovered it and later led follow-up observations with the James Webb Space Telescope, described it as one of the most appealing possible targets for Webb, precisely because of how uniquely well-suited the telescope is to studying something this cold and this close. The coldest brown dwarfs are brightest at infrared wavelengths and extremely faint and difficult to observe at visible wavelengths, so they are very well suited for JOST. He added that it was such an obvious object to observe with JOST that it was selected by multiple teams for guaranteed time observations with all of the instruments on JOST, meaning multiple independent research groups all separately requested time to study the very same faint, cold object the moment the telescope became available, each hoping to be the first to pull real chemical detail out of its nearly invisible glow. So sitting essentially in our own cosmic backyard, closer to Earth than the vast majority of stars visible in any night sky chart, is an object cold enough to grow water clouds, nearly invisible to human eyes, and undetected by astronomy for the entire history of the field, until an infrared space telescope finally caught its faint glow in 2014. It's a reminder that dark doesn't always mean far away or exotic. Sometimes it just means quiet enough and cold enough to have been sitting there the whole time, close enough to touch on a cosmic scale, waiting for the right kind of telescope to finally notice it. What you're actually looking at in that picture. Before moving on to the second black hole ever photographed, it's worth pausing on something that trips a lot of people up when they first see one of these images. What exactly is the dark part in the middle, and why does it look the way it does? It's a question worth answering carefully, because the images themselves get shared constantly online, usually without any explanation of what the glowing ring and the dark center actually represent, leaving a lot of people with the vague, slightly wrong impression that they're looking at some kind of tunnel or doorway rather than a shadow cast by gravity itself. A black hole itself, the actual object, the point where matter has been compressed down to a level current physics can't fully describe, is called a singularity, and it is genuinely invisible, in the most literal sense possible. No telescope, current or hypothetical, will ever photograph a singularity directly, because no light escapes from anywhere near it to reach a camera. What the Event Horizon Telescope images actually show isn't the black hole itself, it's the black hole's shadow, a dark silhouette cast against a bright backdrop of glowing, superheated gas that's swirling around the black hole in what's called an accretion disk, material being pulled inward, compressed and heated to extreme temperatures before it eventually crosses a boundary called the event horizon, the point of no return, beyond which not even light has enough energy to climb back out. The dark circle you see in those images is slightly larger than the event horizon itself, because gravity near a black hole is so strong that it bends the path of light passing nearby, a phenomenon predicted by general relativity and confirmed by these very images. Light from the glowing gas behind the black hole, gas that would otherwise be completely hidden from view, gets bent around the edges of the shadow and focused into that bright ring you see surrounding the dark center. In a strange sense, you're seeing light from both in front of and behind the black hole simultaneously, folded together by gravity into a single glowing circle, wrapped around a darkness that light itself cannot escape. There's a specific boundary involved in that bending too, called the photon sphere, a razor-thin region where light can theoretically orbit the black hole in a perfect circle before either escaping or spiraling inward. And the dark shadow captured in these images is closely tied to the size of that photon sphere rather than the event horizon itself, meaning the black shape you actually see in the picture is measurably larger than the true point of no return sitting hidden inside it. This is why these images represent such a direct test of Einstein's general theory of relativity. The exact size, shape, and brightness pattern of that ring is something physicists could calculate mathematically decades before anyone had the technology to actually observe one. When the Event Horizon Telescope's images came back matching those decades-old predictions with remarkable precision, first for M87 in 2019 and then for Sagittarius A in 2022, it confirmed that a theory built entirely out of equations, describing conditions no human being will likely ever directly experience, accurately describes what happens at the single darkest, most extreme boundary that exists anywhere in the observable universe, the monster in our own backyard. If M87 proved that black holes could be photographed, the next challenge was closer to home, and in a strange way, it turned out to be much harder. On May 12, 2022, the Event Horizon Telescope collaboration released the first ever image of Sagittarius A, the supermassive black hole sitting at the exact center of our own Milky Way galaxy. But that 2022 image was really the final chapter of a much longer story. Since the early 1990s, two separate research teams, one led by German astrophysicist Reinhard Genzel and one led by American astronomer Andrea Ghez, had each been tracking the motion of stars orbiting the galactic center with increasing precision, using the world's largest telescopes and pioneering new techniques, like adaptive optics, to cancel out the blur caused by Earth's own atmosphere. Both teams focused especially on one particular star, designated S2, watching it whip around an apparently empty patch of space at astonishing speed. If that patch of space had simply contained an ordinary, spread-out cluster of stars and gas, S2's orbit would have looked unremarkable. Instead, it behaved exactly as it would if it were slingshotting around an invisible object roughly 4 million times the mass of the Sun, compressed into a region smaller than our own solar system. In 2018, Genzel's team also detected gravitational redshift in light coming from S2 as it passed closest to that invisible object, direct confirmation of Einstein's general relativity operating exactly as predicted, right at the heart of our own galaxy. That decades of patient, independent stellar tracking earned Genzel and Gez a share of the 2020 Nobel Prize in Physics, awarded for the discovery of a supermassive compact object at the center of our galaxy, alongside physicist Roger Penrose, honored separately for proving mathematically that black holes are a genuine, unavoidable consequence of general relativity, rather than just a theoretical curiosity. So by the time the Event Horizon Telescope finally released its 2022 image, the scientific case for Sagittarius A being a black hole was already about as solid as physics gets. What that image actually delivered wasn't new proof that something massive and invisible sat at our galaxy's center, that had already been settled and formally recognized with astronomy's highest honor 2 years earlier. What it delivered was the thing decades of orbital tracking could never provide: an actual picture, however faint and reconstructed, of the shadow itself, the closest humanity has ever come to actually seeing, with our own instruments, the black hole quietly anchoring the galaxy we call home. Sagittarius A is estimated at about 4 million times the mass of our Sun, packed into a region small enough to sit at the center of our galaxy, roughly 27,000 light-years from where you're sitting right now. Producing that single image required linking together 8 radio observatories scattered across the entire planet, effectively turning Earth itself into one enormous telescope, exactly as it had for M87. 3 years earlier, the data behind the image was actually recorded back in April of 2017, the same observing campaign that captured M87, meaning it took about 5 years of processing and analysis before the Sagittarius A picture was ready to share with the world. And the light captured in that data had already been traveling toward Earth for tens of thousands of years before it ever reached those telescopes. So in a very real sense, everyone looking at that image in 2022 was looking at ancient light, twice removed from the present moment, a shadow of something that had already been sitting there quietly for far longer than our species has existed. Here's what makes this story genuinely surprising though. Despite Sagittarius A being vastly closer to Earth than M87, and despite the collaboration already having a successful black hole image under their belt, imaging our own galaxy's black hole turned out to be considerably harder. The reason comes down to size, and specifically, how quickly things move around an object of a given mass. Because M87's black hole is so much larger, at roughly 1,600 times the mass of Sagittarius A, gas orbiting it takes days to weeks to complete a full loop, moving at nearly the speed of light either way, but circling a much bigger track. Sagittarius A, despite still being millions of times more massive than our Sun, is comparatively tiny, and gas around it completes an entire orbit in a matter of minutes. EHT scientist Chi-Kwan Chan explained the difference plainly. The gas in the vicinity of the black holes moves at the same speed, nearly as fast as light, around both SGR-A and M87. But where gas takes days to weeks to orbit the larger M87, in the much smaller SGR-A, it completes an orbit in mere minutes. The innermost material takes roughly 30 minutes to circle Sagittarius A, compared to about 30 days for M87. That means the object the astronomers were trying to photograph was actively changing shape while they were still collecting the data needed to photograph it. Chan compared the challenge to trying to take a clear picture of a puppy quickly chasing its tail. Vincent Fish of MIT's Haystack Observatory put it just as simply: SGR-A is changing over minutes, so the data is jumping all over the place. It's the astronomical equivalent of trying to take a long exposure photograph of a toddler who refuses to sit still, except the toddler is a supermassive black hole and the exposure has to span hours of observation time from telescopes on opposite sides of the planet, all needing to see a stable enough picture to combine. While nearly all of the M87 images produced by different processing methods looked essentially the same, that consistency broke down completely with Sagittarius A. To solve the problem, The team had to develop entirely new imaging tools, built specifically to account for the constant motion, then average together thousands of possible reconstructed images, all of which fit the raw data equally well, and identify the features that showed up consistently across all of them, while suppressing the ones that only appeared occasionally due to the object's constant flickering and rearranging. It's worth remembering that the researchers weren't just building a picture from scratch. They were building thousands of plausible pictures simultaneously, all consistent with the same messy data, and then trusting only the features that refused to disappear, no matter which version they looked at. A painstaking process of elimination applied not to a single image, but to an entire library of competing possibilities, run through supercomputers for months before a final consensus picture could be trusted enough to publish. The result, after 5 years of work on top of an already difficult prior success, is a single glowing ring around an absence, sitting quietly at the heart of the galaxy we call home, and it had been there the entire time, long before anyone on Earth had the technology to notice, patiently existing at the center of every night sky any human has ever looked up at, invisible in plain sight for the entire span of human history until a global network of radio dishes finally caught up to it. A quick sense of scale. Before we go any further, it's worth stopping for a moment to actually line up everything covered so far, because on their own, big numbers tend to blur together, and it's easy to lose track of just how differently sized these objects really are relative to each other. Start small, relatively speaking. TRAS 2b, the darkest known planet, is roughly the size of Jupiter, a large gas giant, but still just a planet, a single world orbiting a single star. Zoom out, and Sagittarius A, the black hole at the center of our entire galaxy, comes in at about 4 million times the mass of our Sun, a single object outweighing millions of stars combined, yet compact enough that its innermost material still completes an orbit in about half an hour. Zoom out again, and M87, the first black hole ever photographed, sits at roughly 6.5 billion solar masses, well over 1,000 times heavier than Sagittarius A, anchoring an entire separate galaxy 55 million light-years away. And then there's 2N618, plausibly touching 66 billion solar masses by the higher estimate, a single black hole whose mass rivals the combined mass of every star in the Milky Way, a galaxy that itself contains hundreds of billions of individual suns. Now flip from mass to sheer size. The Coalsack Nebula, close enough to see with the naked eye, spans somewhere around 50 light-years across. WISE 0855, by contrast, isn't spread across any meaningful distance at all. It's a single compact object, roughly the size of Jupiter, just sitting remarkably close to us, at barely 7 light-years away. The Boötes void, the Great Nothing, stretches roughly 250 to 330 million light-years, large enough to swallow the Milky Way billions of times over. The Great Attractor's home structure, the Laniakea supercluster, spans about 500 million light-years and contains roughly 100,000 galaxies, our own included, all slowly flowing toward the very same gravitational basin hidden behind our galaxy's dust. The KBC void, if it holds up under continued study, may stretch even further, close to 2 billion light-years across, with our entire galaxy sitting somewhere inside it. And the Eridanus supervoid, linked to the cold spot in the universe's oldest light, spans an estimated 1.8 billion light-years on its own, a void so large that light passing through it measurably cools down by the time it reaches us on the other side. And underneath all of that sits the darkest chapter of all, the cosmic dark ages, which isn't a size or a mass at all, but a stretch of time, several 100 million years, during which literally none of the light-emitting objects on this list, no black holes glowing with infalling gas, no dying stars breathing out ultra-cold nebulae, no planets glowing red with their own residual heat, existed anywhere in the universe at all. Every single other entry on this list needed that darkness to end first, needed those first stars to finally ignite, before there could be enough raw material, enough heavy elements forged in stellar furnaces, enough gravity concentrated into black holes, for any of the rest of this list to eventually come into existence. With that scale in mind, let's head back out to the objects themselves, starting with the one you don't need billions of light-years of distance to be affected by, because it might be steering our entire galaxy right now. the massive thing hidden behind our own galaxy. Every dark place covered so far has been far from Earth, tens of millions or billions of light years away. This next one is different. It's close, astronomically speaking, and we can't get a clear look at it for a strange, almost embarrassing reason. Our own galaxy is standing directly in the way, a piece of cosmic irony that took decades of patient work to even properly diagnose. It's called the Great Attractor, and it was first noticed not by seeing it, but by watching everything around it move. In 1986 and 1987, a team of 7 astronomers, Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner, published research so unexpected that colleagues quickly nicknamed the group the Seven Samurai. Using a technique for estimating galaxy distances based on the relationship between a galaxy's size, brightness, and the speed of its stars, the team measured motion for roughly 400 elliptical galaxies and found something nobody had predicted. Rather than moving in random directions, as the universe's ordinary expansion would suggest, galaxies across a huge stretch of the sky were all flowing in a coherent, shared direction, drifting toward the same unseen point in space, at speeds later estimated around 600 kilometers per second relative to the cosmic microwave background. The team coined the term Great Attractor for whatever unseen concentration of mass was causing that shared motion. Those extra, unexplained motions are called peculiar velocities, and researchers found they ranged from roughly 700 kilometers per second toward the source, up to 700 kilometers per second away from it, depending on exactly where a given galaxy sat, relative to whatever was doing the pulling. The estimated pull is almost impossible to picture. The concentration of mass responsible is believed to be on the order of 10 to the 16th power solar masses, a 1 followed by 16 zeros, worth of suns, and it appears to be drawing not just the Milky Way, but roughly 100,000 other galaxies toward it, forming the gravitational anchor point of an enormous structure called the Laniakea supercluster, the vast web of galaxies our own Milky Way belongs to. One team studying it described the pull as gravitationally equivalent to 1,000,000 billion suns worth of force. Whatever this thing is, it's massive enough to be reshaping the trajectory of 100,000 galaxies, our own included, and for decades, nobody could actually look directly at it. The problem is a simple one, once you understand it, and it comes down to geography rather than physics. The Great Attractor happens to sit almost exactly behind the flat disk of our own galaxy, from our vantage point here on Earth. Astronomers call this obscured strip of sky the zone of avoidance, a term coined by the astronomer Edwin Hubble himself, referring to the region near the galactic plane where the Milky Way's own stars, gas, and dust are so thick that they block our optical view of almost everything behind them. If you want an unbiased view of the distant universe, you avoid pointing your telescope in that direction, because all you'll see is a wall of foreground clutter belonging to our own galaxy, and it just so happens that the single most gravitationally significant structure in our cosmic neighborhood is sitting directly behind that wall. For years, that meant astronomers could measure the Great Attractor's effects with total confidence, watching galaxy after galaxy get tugged in its direction, while being functionally unable to actually see what was doing the pulling. It's a strange position to be in scientifically, knowing something enormous is there, being able to calculate roughly how massive it is just from the way it bends the paths of everything nearby, and still not being able to point a normal telescope at it and get a picture back. The way around the problem turned out to be light itself, just not the kind our eyes can see. Optical light, the visible wavelengths astronomers normally rely on, gets almost completely absorbed by the Milky Way's dust. But radio waves and near-infrared light pass through that same dust far more easily. The same basic principle that lets an X-ray see through skin to photograph the bone underneath. Using CSIRO's Parkes radio telescope in Australia, fitted with an innovative new receiver, an international team led by Professor Lister Staveley-Smith of the International Centre for Radio Astronomy Research finally managed to peer straight through the zone of avoidance and catalogue what was actually back there. The results, published in 2018, turned up 883 galaxies in the surveyed region, roughly a third of which had never been recorded by any previous survey, hiding in plain sight behind the glow of our own Milky Way this entire time. Some of them large, ordinary galaxies that simply happened to sit in exactly the wrong direction from Earth to ever be noticed by generations of astronomers scanning the visible sky. Follow-up work has kept chipping away at the mystery since then. Researchers have identified the Great Attractor as not one single object, but a combination of structures, including a rich, massive galaxy cluster called the Norma cluster, sitting at its core, comparable in scale to the well-known Coma cluster, but considerably closer to us, along with a larger, more distant structure called the Vela supercluster. In 2022, astronomers using near-infrared observations identified yet another previously hidden cluster of galaxies in the same general direction, a structure whose light had been traveling toward us for roughly 2.7 billion years, and which is estimated to weigh somewhere between 45 and 50 times the mass of the entire Milky Way on its own. More recent work, published in 2024 using South Africa's Meerkat radio array, has continued mapping galaxies in the zone of avoidance in even greater detail, slowly filling in a region of the sky that spent most of the history of astronomy as a complete blank. There's still real uncertainty about the full picture, though. Researchers have pointed out that the reconstructed mass distribution behind the zone of avoidance doesn't always line up perfectly with where the visible galaxies actually are, a mismatch that raises a genuinely open question. Does light reliably trace mass everywhere in the universe, or are there regions where the two decouple from each other in ways we don't yet understand? The existence of the Great Attractor as a single coherent structure has even been formally questioned in the scientific literature, though the accumulated observational evidence, X-ray data, galaxy surveys, radio catalogs, and the consistent peculiar velocity measurements has only grown stronger over time. There's a follow-up chapter to this story that helped put the Great Attractor into its proper context, one that came nearly 3 decades after the original discovery and finally gave the whole structure a name people outside of academic astronomy could actually use. In September 2014, astronomer R. Brent Tully of the University of Hawaii at Manoa led an international team that used the peculiar velocities of thousands of galaxies, more than 8,000 of them, measured out to roughly 400 megaparsecs, to map something no one had ever fully defined before: the actual boundaries of the entire supercluster our galaxy belongs to. Rather than identifying the structure the old way, by eye, looking for places where galaxies simply appeared to clump together on the sky, Tully's team defined it by motion instead, tracing which galaxies were gravitationally flowing toward the same shared basin of attraction, and where those flows diverged toward some other structure entirely. The result, published as the cover story of the journal Nature, was a newly defined supercluster spanning roughly 500 million light-years and containing an estimated 100,000 galaxies, with a combined mass on the order of 10 to the 17th power times the mass of our Sun. They named it Laniakea, a Hawaiian word meaning immense heaven or open skies, suggested by Nawaa Napoleon, an associate professor of Hawaiian language, chosen partly to honor the Polynesian navigators who once used the stars themselves to cross the Pacific Ocean. Tully described the significance of the discovery plainly. We have finally established the contours that define the supercluster of galaxies we can call home. This is not unlike finding out for the first time that your hometown is actually part of a much larger country that borders other nations. And sitting at the gravitational heart of that entire immense structure, the basin every one of those 100,000 galaxies is slowly flowing toward, is the very same Great Attractor, still largely hidden behind our own galaxy's disk, still being mapped one radio survey at a time. So somewhere behind the stars of our own galaxy, hidden not by billions of light-years of distance, but simply by the accident of our position inside a dusty spiral disk, sits one of the most gravitationally significant structures in our entire local universe, quietly pulling on 100,000 galaxies, including our own, mapped indirectly for decades before anyone managed to catch even a partial glimpse of what was actually causing the pull. It's proof that a dark place doesn't have to be far away, or empty, or cold. Sometimes the thing you can't see is enormous, right next door, and hidden by nothing more exotic than your own house standing in the way. Notice something about the last 2 entries on this list. Both the Great Attractor and the 2 black holes we've already covered share a strange trait. They were understood mathematically, through the way they influenced everything around them, long before anyone could actually see them directly. Astronomers spent years tracking galaxies being tugged toward the Great Attractor without ever pointing a telescope directly at its source. They spent decades watching stars orbit an invisible object at the center of our galaxy before the Event Horizon Telescope finally produced an image of the shadow those stars were circling. Darkness, it turns out, doesn't always mean absence of evidence. Sometimes the evidence is overwhelming. Decades of consistent, repeatable measurement, and the only thing actually missing is a direct look. The heaviest black hole ever measured, if Sagittarius A, feels enormous at 4 million solar masses, and M87 feels almost incomprehensible at 6.5 billion. The next entry on this list will make both of them look almost small by comparison. This is a black hole so massive that astronomers have had to invent a whole new category just to describe it. Its name is TON 618, and its story starts with a case of mistaken identity. The name itself is a leftover from routine cataloging. TON stands for Tonantzintla, the Mexican observatory where it was recorded, and 618 simply marks its position, the 618th entry, in a survey list of faint blue stellar objects, the astronomical equivalent of a filing number rather than anything meant to sound dramatic. In 1957, Mexican astronomers Braulio Iriarte and Enrique Chavira, working at the Tonantzintla Observatory, catalogued it during a survey of faint blue stars scattered far from the plane of the Milky Way. As far as they knew at the time, they were looking at a distant, unremarkable white dwarf. The problem was, quasars, the class of object TON 618 actually belongs to, hadn't even been discovered yet. Astronomers wouldn't recognize quasars as their own category of extremely bright, distant, black hole-powered objects until 1963, 6 years after TON 618 had already been logged as just another faint blue dot in a routine survey, one of thousands of entries in a catalogue nobody thought twice about at the time. Once astronomers understood what they were actually looking at, the numbers involved became almost difficult to process. TON 618 sits somewhere around 10.8 billion light-years away, based on Guinness World Records figures, though other estimates that account for the ongoing expansion of the universe place its co-moving distance closer to 18.2 billion light-years. It's believed to have formed roughly 3.4 billion years after the Big Bang, meaning the light we're seeing left that object when the universe itself was still relatively young, barely a quarter of its current age, a snapshot mailed to us from a much earlier chapter of cosmic history. The mass estimate is where things get genuinely contested, and it's worth being upfront about that, rather than picking one number and pretending it's settled science. The most widely cited figure comes from a 2004 study led by Ohad Shemer, which measured the width of a specific emission line in the quasar's light, called the H-beta line, and used that to estimate a black hole mass of roughly 66 billion times the mass of our Sun. Guinness World Records still lists that 66 billion figure as the record for the most massive black hole ever measured, but a more recent analysis in 2019, led by G and colleagues, used improved methods and revised that estimate down to approximately 40.7 billion solar masses. The two figures differ by nearly a factor of 2, which says less about sloppy science and more about just how difficult it is to weigh an object this far away using nothing but the width of light streaming off its edges, a bit like trying to weigh a distant ship by measuring how much its wake ripples the shore. Even taking the lower of those two numbers, the comparison is almost impossible to wrap your head around. The Milky Way galaxy contains somewhere between 200 and 400 billion stars, with a combined stellar mass of roughly 64 billion times the Sun. That means the black hole at the heart of TON 618, by the more conservative estimate, comes close to matching the mass of every single star in our entire galaxy, combined, concentrated into one object. And it's roughly 15,300 times more massive than Sagittarius A, the black hole sitting at the center of our own galaxy that took 5 years just to photograph, and still more than 6 times the mass of M87, the very first black hole ever imaged by humanity. The physical scale of the thing matches the mass. Depending on which estimate you use, TON 618's event horizon, the boundary past which nothing, not even light, can escape, spans somewhere between 1,300 and 2,600 astronomical units in radius, which works out to roughly 195 to 390 billion kilometers. Guinness World Records described it this way: the black hole is big enough to swallow every planet in our entire solar system more than 40 times over, in terms of the sheer volume of space it occupies, spanning something like 30 to 40 times the width of our own solar system. If you replaced our Sun with TON 618, the event horizon alone would extend roughly 40 times farther than the orbit of Neptune, engulfing the entire solar system as we understand it, and leaving nothing but darkness where every planet used to be. Light itself, moving at roughly 300,000 kilometers per second, the fastest anything in the universe can travel, would still need somewhere between roughly 2 and 4 weeks just to cross from one side of that event horizon to the other. An object so large that its own boundary takes longer to traverse at light speed than it takes light to travel from the Sun all the way out to Pluto, and most of the way back. It's also almost unbelievably bright. TON 618 shines somewhere between 100 and 140 trillion times more luminously than our Sun, making it, quite literally, brighter than an entire galaxy's worth of stars combined, with material in its surrounding accretion disk clocked at speeds up to 10,500 kilometers per second as it spirals toward the black hole, a significant fraction of the speed of light itself, compressed and heated by friction and gravity to temperatures and pressures that make the disk shine far more intensely, pound for pound, than the nuclear furnace at the heart of any single star ever could. In 2021, follow-up observations using the ALMA telescope array confirmed something else surrounding this object: a massive cloud of neutral hydrogen gas called a Lyman alpha blob, stretching roughly 330,000 light-years across, more than double the width of the entire Milky Way, glowing under the intense radiation pouring out of the quasar at its center. It's worth asking, even briefly, how a black hole gets this big in the first place, because the number alone doesn't explain the process behind it. The general picture astronomers work with is that supermassive black holes grow over cosmic time through two main channels, swallowing gas and dust that spirals inward from a surrounding accretion disk, the same glowing material captured in the EHT images of M87 and Sagittarius A, and merging with other black holes when their host galaxies collide. Both processes take enormous stretches of time, and both have physical speed limits, since gas falling toward a black hole releases radiation that can push back against further infalling material, throttling how quickly the black hole can actually feed. For an object like TON 618 to have accumulated tens of billions of solar masses within roughly the first 3.4 billion years of the universe's history, well before galaxies had anywhere near as much time to grow and merge as they do today, its black hole would have needed to grow unusually fast, which is exactly why objects like it remain such active subjects of ongoing research into how the very earliest, most massive black holes managed to get so big, so quickly, in a universe that was still relatively young. Given numbers this extreme, some astronomers have started arguing that supermassive simply isn't a big enough word anymore, and have proposed a new category, ultramassive, reserved specifically for black holes in this weight class. TON 618 isn't even alone up there. Other contenders like Phoenix A, a black hole called SDSS J140821 67 plus 025733.2, and the black holes inside the galaxies Holmberg 15A and IC 1101 all get mentioned in the same conversation, each estimated somewhere in the tens of billions of solar masses. But TON 618, sitting there since before astronomers even had a name for what it was, remains one of the most commonly cited record holders. A single point of light first mistaken for a faint, unremarkable star, and instead turning out to be one of the single heaviest objects ever confirmed to exist, hiding in plain sight in a decades-old catalogue for years before anyone realized what they'd actually written down. The cold spot that shouldn't exist. For the next stop on this journey, we're going all the way back to the beginning of everything, to a faint glow that fills the entire universe, and to one specific patch of that glow that has puzzled cosmologists for years, and to a method astronomers use to map something that, by definition, cannot be seen at all. That glow is called the cosmic microwave background. the leftover radiation from the Big Bang itself, spread evenly across every direction you can point a telescope. It's essentially a baby picture of the universe, frozen in place from roughly 380,000 years after everything began, back when the universe first became transparent enough for light to travel freely. And when astronomers map it out in detail, it's remarkably uniform, tiny fluctuations in temperature scattered fairly evenly across the sky. Except for one place. One patch of the cosmic microwave background is noticeably, stubbornly colder than it should be. Astronomers call it, without much poetic flourish, the cold spot. For years, nobody had a solid explanation for why this one region would be different from everywhere else. But the leading theory today points to something enormous sitting directly in front of it. From our perspective, an almost unimaginably large void called the Eridanus supervoid. Located in the constellation Eridanus, this supervoid is described as a massive, elongated, cigar-shaped region of space, stretching roughly 1.8 billion light-years across, containing about 30% less matter than the space surrounding it. Its center sits roughly 2 billion light-years from Earth, making it the single largest underdense region in our broader corner of the universe. In December 2021, a team working with the Dark Energy Survey, an international collaboration involving roughly 300 scientists across 25 institutions in 7 different countries, led by astrophysicist András Kovács of the Instituto de Astrofísica de Canarias, confirmed the connection. The Dark Energy Survey itself is a massive multi-year project, using a custom-built digital camera mounted on the Blanco telescope specifically to map hundreds of millions of galaxies across a huge swath of the southern sky. Originally designed to study dark energy's role in the universe's expansion, but well-suited, as a byproduct of that same data, to hunting for exactly this kind of large-scale underdensity. But to understand how they did it, it helps to understand a strange fact about dark matter itself. We cannot see it directly, not with any telescope, no matter how powerful. It doesn't emit light, absorb light, or reflect light. What it does do is bend light through its gravity, the same way any massive object warps the space around it, a phenomenon called gravitational lensing. Picture looking at a background pattern through a thick, uneven pane of old glass. The glass itself might be invisible, but you can map exactly where it is and how thick it is in different spots, just by studying how the pattern behind it gets distorted, stretched, and smeared as light passes through. That's essentially what astronomers do with dark matter. By carefully measuring how the shapes of distant background galaxies appear subtly warped and distorted, sheared just slightly out of their natural rounder shapes, they can reconstruct a map of the invisible mass responsible for the warping, without ever directly seeing the thing doing the bending. It's a method built entirely on inference, reading the shadow of something to figure out the shape of what's casting it. Using a catalogue of luminous red galaxies and gravitational lensing data gathered with the Blanco telescope high in the Chilean Andes, the Dark Energy Survey team built a detailed map of dark matter in the exact direction of the cold spot. What they found lined up almost perfectly. The Eridanus supervoid really is there, really is enormous, and really is sitting directly along the line of sight to that cold patch in the ancient light of the universe, showing up as the single most significant large-scale underdensity in their entire reconstructed map, detected with a statistical confidence high enough that researchers described it as unlikely to be a coincidence. The physical explanation for the connection goes something like this. Light passing through a giant, matter-poor void loses a small amount of energy along the way, through something astronomers call the integrated Sachs-Wolf effect, and that tiny energy loss shows up, billions of years later, as a slightly cooler reading in our instruments. It's a real, measurable phenomenon, and it makes intuitive sense that a void this size sitting in this direction could leave a mark on the background radiation passing through it, a faint cosmic bruise left by light, dragging itself through a region with less gravity to hold on to. But it's worth being honest about the limits of this discovery too, because the researchers themselves were. According to the Dark Energy Survey's own findings, this effect, under the universe's standard model of physics, can only account for somewhere between 10 and 20% of the actual temperature drop observed in the cold spot. The void's gravitational lensing signal even came out about 30% weaker than computer simulations predicted it should be, which means The Eridanus supervoid is very likely part of the answer. A real, confirmed, physical structure sitting in exactly the right place, but not the entire answer. Something about the cold spot's full depth still isn't accounted for, and that gap remains an open question in cosmology today. A mystery hiding inside a void, hiding inside the oldest light in the universe. 3 layers of unresolved darkness stacked directly on top of each other. It's also worth noting that the Eridanus supervoid explanation isn't the only idea that's ever been floated for the cold spot, and understanding why other ideas were even considered says something about how stubborn this particular puzzle turned out to be. Because a purely random statistical fluctuation of this size and depth would be considered fairly unlikely under the standard cosmological model, some researchers have explored far more speculative alternatives over the years, including proposals involving exotic early universe physics, and even, at the more theoretical end of the spectrum, hypothetical models involving structures from before or beyond our own observable universe. None of these more exotic ideas have anywhere near the observational support that the Eridanus supervoid explanation has earned through direct, repeated measurement, and most cosmologists treat them as interesting theoretical exercises rather than serious contenders. But their mere existence in the scientific conversation says something about how genuinely strange the cold spot has been to explain. Strange enough that for years, physicists were willing to seriously entertain nearly anything that might account for it, before the patient, unglamorous work of surveying galaxy positions and mapping gravitational lensing finally turned up a real, physical, confirmable structure sitting exactly where the anomaly pointed. The darkest chapter in the universe's entire history. Every dark place we've covered so far has been a location, somewhere you could point a telescope and, eventually, see something. This last one is different. This is a stretch of time, an entire era of the universe's history, during which there was, quite literally, nothing to see anywhere at all. Scientists call it the Cosmic Dark Ages, and to understand it, you have to go back to the very beginning. For the first 380,000 years after the Big Bang, the universe was an unimaginably hot, dense soup of particles, protons, neutrons, and electrons, bouncing around in a state of ionized plasma, so chaotic that light itself couldn't travel freely. Photons kept slamming into free electrons before they could get anywhere, the same way you can't see far through a thick fog. The universe, in its earliest moments, was completely opaque. Then, as the universe expanded and cooled, something changed. Protons and electrons finally settled down enough to combine into stable, neutral atoms of hydrogen and helium, an event cosmologists call recombination. A slightly misleading name, since those particles had never actually been combined before, but the term stuck anyway. Once those electrons were locked into atoms instead of drifting freely, light stopped scattering off them constantly, and for the first time, photons could travel in straight lines across the universe without immediately crashing into something. The fog lifted. The universe became, in a physical sense, transparent, all at once, everywhere, in a single cosmic transition that unfolded over a relatively short span of cosmic time, given how long the universe has existed since. That very first burst of light that was finally set free at that moment is the same cosmic microwave background we just discussed in the cold spot section, humanity's oldest possible photograph of the universe. But transparent doesn't mean lit. There was nothing yet actually producing new light. No stars had formed, no galaxies existed. The universe had become clear enough to see through, but there was nothing to see, just vast, slowly cooling clouds of neutral hydrogen and helium gas, drifting through the dark for what NASA describes as potentially several 100 million years. This period, sitting between the release of that first ancient light and the ignition of the first stars, is the Cosmic Dark Ages, and it may be the single darkest chapter the universe has ever gone through, a stretch of cosmic time with no starlight anywhere, at any point, in any direction. Eventually, gravity did what gravity does. Slight, tiny density fluctuations left over from the earliest moments of the universe slowly grew stronger as matter clumped together, and in the densest of those clumps, hydrogen gas finally compressed enough to ignite nuclear fusion for the first time. Theoretical models suggest these first-generation stars, astronomers call them population 3 stars, were monstrous by modern standards. somewhere between 30 and 300 times the mass of our Sun, and up to millions of times brighter, burning through their fuel in a cosmic blink, just a few million years before detonating as supernovae. Part of what made them so massive in the first place is thought to be the chemistry of the early universe itself. The only elements that existed before those first stars formed were hydrogen, helium, and faint traces of lithium, since every heavier element, carbon, oxygen, iron, and everything else that makes up planets and people, had to be forged later inside the cores of stars like these and flung back out into space by their eventual deaths. Without heavier elements to help gas clouds cool and fragment into smaller pieces the way modern star-forming clouds do, the earliest clouds of gas are thought to have collapsed into far fewer, far larger stars than the universe produces today. Nobody has ever directly observed one of these first stars. Everything we know about them comes from theoretical modeling, since they're believed to have formed and died within the first billion years of the universe's history, at distances so extreme that even our best telescopes struggle to catch a glimpse. Those first stars ended the Dark Ages the same way a lit match ends a blackout, one small point of light at a time. Their intense ultraviolet radiation began splitting the surrounding neutral hydrogen gas back apart into free protons and electrons, a process astronomers call reionization, the mirror image of the recombination event that had plunged the universe into darkness in the first place, except spreading outward gradually from countless individual points of light, rather than happening everywhere at once. It was a patchy, gradual process, pockets of ionized gas expanding and merging with neighboring pockets, like bubbles of light slowly spreading and joining together across a universe that was still overwhelmingly dark. And current evidence suggests it began taking hold by the time the universe was around 1 billion years old and had largely finished by the time it reached roughly its current billion and change year mark of that early era. Though the precise timeline and the exact sources responsible for finishing the job, whether it was ordinary stars, the accretion disks of early black holes, or some mix of both, remain genuinely unresolved questions in cosmology. Because there were no bright stars and no glowing plasma clouds during the Dark Ages themselves, this entire chapter has been almost impossible to observe directly. There's essentially only one type of signal researchers can hunt for from that era, something called the 21 centimeter line, a very specific, very faint wavelength of light produced by the way hydrogen atoms flip their internal spin state, essentially a tiny quantum flicker happening inside the neutral hydrogen gas that filled the universe at the time. It's an incredibly weak signal, and by the time it reaches our telescopes today, it's been stretched dramatically by the expansion of the universe, redshifted down into low-frequency radio wavelengths that are genuinely difficult to detect against all the background noise Earth itself produces. Everything from human radio transmissions to interference generated by our own planet's ionosphere. Researchers using instruments like the Murchison Wide Field Array in Western Australia, a radio telescope deliberately built in one of the most radio-quiet locations on the planet, specifically to reduce that kind of interference, have spent years, in some cases combining a full decade's worth of collected data, just trying to isolate a clean signal from this period. One recent line of research using that telescope found evidence that the tail end of the Dark Ages, right as the first structures were beginning to form, was dark, but apparently not as cold as some models had predicted, an early hint that our theoretical picture of this era still has real gaps in it. The signal researchers are chasing is so faint and so easily buried under noise that entire research careers have been built around the specific challenge of statistically extracting it, a project not unlike trying to hear a single whispered word from the back of a packed stadium, using only a microphone left running in the parking lot outside. There's a more recent piece of this story worth adding too, because it's actively unfolding as recently as the past couple of years. NASA's James Webb Space Telescope was specifically designed with an eye toward this exact era, built with infrared instruments sensitive enough to catch the incredibly faint, heavily redshifted light of the very first galaxies, and it has been breaking its own distance records again and again since it began science operations. In October 2023 and January 2024, the JUICE Advanced Deep Extragalactic Survey Team, an international collaboration co-led by astronomer Brant Robertson, confirmed a galaxy called JADES GS Z140, observed as it existed just 290 to 300 million years after the Big Bang, making it, at the time, the most distant, and therefore the youngest, galaxy ever confirmed. Robertson called the discovery completely unanticipated, adding, "It was likely to be seen as the most significant extragalactic discovery with JUST to date." Researcher Kevin Heinlein described his own reaction to finally confirming the record. "I just laughed. I had to get up from my office chair and walk down the hallway and look at the faces of the other JADE scientists. The galaxy itself turned out to be strange by early universe standards too, spanning over 1,600 light-years and shining unexpectedly bright for something so early and so small. A puzzle researchers are still working through. That record didn't last. In 2025, a separate research team led by astronomer Peter van Dokkum announced an even earlier galaxy, informally nicknamed MOM-Z14, short for Mother of All Early Galaxies, observed as it existed just 280 million years after the Big Bang, roughly 50 times smaller than the Milky Way, with Van Dokkum noting the discovery was one JUST was not expected to find, at least not at this stage of the mission, and that astronomers have found, very roughly, over 100 more relatively bright galaxies in the very early universe than were expected based on pre-JOBSIST observations. The team measured emission lines from the galaxy's light, indicating the presence of elements like nitrogen and carbon, evidence that even at this astonishingly early stage, some chemical enrichment beyond pure hydrogen and helium was already underway, meaning at least a few short-lived earlier generations of stars had already lived, forged heavier elements, and died, all within the first few 100 million years of the universe's entire existence. Every one of these discoveries pushes the observable edge of the Dark Ages just a little further back, chipping away, one confirmed galaxy at a time, at exactly how quickly the universe managed to go from total darkness to its first true light. So somewhere in the deep, deep past, stretching across what may have been several 100 million years, the entire universe sat in total darkness, transparent but empty, waiting. A silence longer than the entire span of time, from the first single-celled life on Earth to right now, this very moment, however long you've been watching this video. No stars, no galaxies, no light at all, apart from the fading, cooling afterglow of the Big Bang itself, slowly red-shifting toward invisibility as the universe stretched out around it. It is, by a wide margin, the single darkest place the universe has ever contained. And it isn't a place you could visit, even with a perfect telescope and unlimited time. It's a chapter that already closed, roughly 13 billion years ago, when the first stars finally lit a match in a universe that had been waiting in the dark since its very first few 100,000 years of existence. Which of these you could actually go look at? Before we wrap up, it's worth separating this list into two very different categories, because most of these places are permanently locked behind professional-grade instruments, and one of them genuinely isn't. The Coalsack Nebula is the one clear exception. If you live in, or ever travel to, the southern hemisphere, and you find yourself under a clear, dark sky away from city lights, you can find it with nothing more than your own eyes. Look for the Southern Cross, the compact, easily recognizable star pattern in the constellation Crux, and the Coalsack sits right beside it, an unmistakable dark patch blotting out part of the Milky Way's glow. No telescope, no special equipment, just clear skies and a dark enough location to actually see the contrast between the Coalsack and the star fields surrounding it. Everything else on this list is a different story entirely. The Botas void and the KBC void aren't objects you point a backyard telescope at and see. They're statistical conclusions drawn from years of professional redshift surveys, cataloging thousands of galaxies and noticing which regions come up short. The Boomerang Nebula's record-setting cold was only measurable using a specialized sub-millimeter radio telescope, and later confirmed with ALMA, an array of enormous radio dishes spread across the high-altitude Chilean desert. TRES 2b and WISE 0855 are both far too faint and far too small, from our vantage point, to resolve with anything short of a space telescope purpose-built for exactly this kind of measurement. And the two black hole images of M87 and Sagittarius A required linking together essentially every capable radio observatory on the planet simultaneously. For years, just to produce two single, static pictures. That contrast is worth sitting with for a second. One of the darkest places in this entire list is something you could photograph on your phone from a dark enough campsite tonight, using nothing but a basic camera and a long exposure. The rest required some of the most sophisticated scientific instruments and collaborations ever assembled by humanity. Global telescope networks, decades of patient survey work, spacecraft designed and launched specifically to detect a few degrees of temperature difference from many light years away. Darkness, as a category, spans that entire range, from something visible to the naked eye on a clear night to something that took half a century of astronomy, working as a global team, just to confirm was actually there. A few questions you might still have. Before we close things out, let's run through a handful of questions that tend to come up once people hear about places like these, using nothing but what we've already covered. Could a void like the Botus void or the KBC void ever swallow a galaxy, the way a black hole does? No. Voids aren't objects with an edge pulling things in. They're simply regions where matter happens to be sparse. Nothing gets consumed by a void, and nothing inside one is in any particular danger because of it. If the Milky Way really does sit inside the KBC void, as the ongoing research suggests it might, that fact alone changes nothing about our galaxy's stability. What it might change is how we interpret our own measurements of the universe's expansion rate, since a lower density neighborhood would gently push nearby galaxies outward over cosmic time, exactly the effect researchers like Indranil Banik have been modeling. Is a black hole actually a hole in space, the way the name suggests? Not literally. The name is a bit of a misnomer, popularized by physicist John Wheeler in the late 1960s. A black hole isn't an empty gap or a tunnel. It's an extraordinarily dense concentration of matter, with gravity so strong that not even light can escape past a certain boundary, the event horizon. What you're seeing in images like the ones of M87 and Sagittarius A isn't a hole at all. It's a shadow, a dark silhouette cast by an object so gravitationally extreme it bends and swallows the light around it. Could TRES 2b or WISE 0855 support any kind of life? Almost certainly not, based on everything covered here. TRES 2b is a scorching hot gas giant with a surface temperature around 1,800 degrees Fahrenheit and no solid surface to speak of. WISE 0855, despite its remarkably cold temperature and likely water clouds, is a failed star, a brown dwarf with a mass several times that of Jupiter, not a rocky planet, and its water is believed to exist as ice clouds high in a cold, Jupiter-like atmosphere, rather than anything resembling a habitable surface. Will the Boomerang Nebula ever lose its title as the coldest place in the universe? Almost certainly, eventually. As covered earlier, research from the National Radio Astronomy Observatory has already found portions of the nebula warming as it ages. The extreme cold is a byproduct of one specific, temporary phase in one dying star's final centuries, not a permanent feature of the object. So the record is expected to fade as that outflow continues to slow and warm over time. And finally, is there possibly an even darker place out there that we simply haven't found yet? Almost certainly, yes. Every single entry on this list was discovered using a specific method, aimed in a specific direction, built to catch a specific kind of signal, whether that's a redshift survey, a submillimeter telescope, a global radio interferometer, or an infrared space observatory. Each new instrument that comes online tends to reveal at least one thing nobody was specifically looking for. There is no particular reason to think the current list is anywhere close to complete. One more, since it tends to come up. If the universe is expanding and stretching light as it goes, will everything eventually redshift itself into total darkness? In the very long run, yes, in a sense. Though on timescales so vast they're difficult to meaningfully compare to anything covered in this video. As the universe keeps expanding, distant galaxies keep receding faster, and eventually, light from galaxies far enough away will be stretched beyond any wavelength our instruments, or any instruments, could ever detect. Stars themselves will also eventually stop forming as galaxies run out of the raw gas needed to build new ones, a process that will play out over trillions of years rather than the mere billions the universe has existed so far. None of that is relevant to human timescales in any practical sense, but it's a reminder that the darkest chapter covered earlier the cosmic dark ages before the first stars, may not be a strictly one-time event in the universe's history. It may simply be the beginning of a much longer story that, billions of years down the line, eventually ends up dark again. Closing. So there you have it, 12 of the darkest places and darkest chapters anyone has ever found, and every one of them got dark for a completely different reason. It's worth walking back through the full list once more, slowly, because taken together, they map out almost every different way the universe knows how to hide something. There was the Bhuta's Void, a region of space nearly 1/3 of a billion light-years across, discovered not by seeing something new, but by carefully proving that something expected simply wasn't there. 60 galaxies standing in for the 2,000 that should have existed. A discovery that took 16 patient years of follow-up counting before anyone could say with confidence just how empty it really was. There was the KBC Void, the far larger, far closer possibility that our own galaxy might be sitting inside a similar underdensity right now, a structure that could either resolve one of the biggest open disagreements in cosmology or turn out to be a statistical mirage once enough data comes in, the subject of active, unresolved debate among cosmologists to this very day. There was the Coalsack Nebula, proof that darkness doesn't require empty space at all. Sometimes it requires the opposite, a cloud so thick with dust that it blots out everything behind it, while quietly incubating the next generation of stars, recognized and storied by human cultures for longer than written astronomy has even existed. There was the Boomerang Nebula, a location so cold it has slipped below the temperature of the universe's own leftover heat, a record that is likely temporary and tied to one specific dying star's final, violent centuries. A record that was calculated on paper before it was ever confirmed with a telescope. There was Tres 2b, a planet that by every measurement should be visible and bright, sitting close enough to its star to be scorched, and instead swallowing nearly every photon that reaches it, for reasons that remain genuinely unexplained more than a decade later. And there was WISE 0855, sitting practically on our doorstep at just over 7 light-years away. A failed star so cold it likely grows its own water clouds, radiating almost entirely in invisible infrared light, and staying completely undetected until 2014, despite being one of our nearest neighbors in the entire universe. Then came the black holes, 3 of them spanning a scale that's difficult to hold in your head all at once, together forming perhaps the single clearest thread running through this entire list. Proof that mathematics, when trusted and followed carefully enough, can describe things decades before any instrument exists capable of actually seeing them. M87. The first one humanity ever managed to photograph, an object whose shadow took a planet-sized virtual telescope and years of careful cross-checked processing just to confirm was really there, decades after Einstein's own equations first predicted something like it could exist. Sagittarius A. Sitting at the center of our own galaxy, ironically harder to image than M87. Precisely because it's smaller and faster, a puppy chasing its tail instead of a slow, steady giant. Its existence already proven beyond doubt years earlier by 2 Nobel Prize-winning teams patiently tracking a single orbiting star. Anton 618, a black hole so massive that the word supermassive stopped being adequate, first logged in 1957 as an unremarkable faint blue star, sitting quietly in a catalogue for 6 years before anyone even had the concept of a quasar available to describe what they'd actually found. There was the Great Attractor, a gravitational anomaly powerful enough to be steering 100,000 galaxies, including our own, hidden for decades, not by distance, but by the simple, almost absurd fact that our own galaxy's dust happened to be standing directly in the way, its true extent only gradually coming into focus through radio and infrared surveys built specifically to see past that obstruction. There was the Eridanus supervoid and the cold spot it's connected to, a billion light-year gap in the cosmic web casting a measurable chill onto the oldest light in the universe, though even the astronomers who confirmed the connection admit it only explains part of the mystery, leaving room for whatever else might be contributing to that cold patch to still be found. And finally, there was the deepest darkness of all, not a place but a stretch of time, several 100 million years, during which the entire universe sat transparent, cooling, and completely unlit, waiting for the very first star to strike its first spark, a darkness so total that every single other entry on this list depended on it ending before any of them could ever exist. What ties all of these together isn't really darkness at all. It's how much we still don't know. Every one of these places, the ones nearly empty and the ones impossibly dense, the ones hidden by distance and the ones hidden by our own galaxy's dust, the ones we can point a telescope at and the ones we can only infer from a faint radio signal stretched across billions of years, raised more questions than they answered when we found them. And most of those questions are still open today, actively being argued over in journals, conferences, and telescope proposal committees right now, this week, while you're watching this. Some of what you just learned might not even be settled by the time you watch this again. TON 618's mass could shift with the next study. The Eridanus supervoid might turn out to explain more, or less, of the cold spot than current estimates suggest. The Great Attractor's true extent is still being mapped, one radio survey at a time, through a wall of stars and dust that has only recently started to become even partly transparent. And the KBC void, the one we might be living inside right now, could either solve one of cosmology's biggest disagreements or quietly fade from the conversation as new data comes in. That's not a flaw in the science. That's the whole point of it. The universe has plenty of dark corners left, some of them empty, some of them unimaginably dense, some of them stretched across entire epochs of time rather than any single point in space, and at least one of them possibly wrapped around the very ground you're standing on. Every time we manage to point a telescope, or a mathematical model, or a patient 20-year survey at one of them, we end up finding something stranger than we expected, and there is no reason to think that pattern is anywhere close to finished. Somewhere out there tonight, there is very likely another dark place nobody has noticed yet, sitting quietly in plain sight, waiting for the right instrument, pointed in the right direction, at the right wavelength, to finally catch it. It's worth remembering too, just how recently most of this list came into focus. The Boötes void is the oldest confirmed discovery here, and even that only dates back to 1981, well within living memory for a large share of the people watching this right now. The first image of any black hole didn't exist until 2019. The image of our own galaxy's black hole didn't exist until 2022. The connection between the Eridanus supervoid and the cold spot wasn't confirmed until December 2021. WISE 0855, despite sitting closer to Earth than the vast majority of the night sky's visible stars, wasn't even detected until 2014. And the record for the most distant, earliest galaxy ever observed, the object that marks the very edge of our direct view into the cosmic dark ages, has been broken twice just in the last couple of years. First in 2024, and then again in 2025, with researchers openly expecting it to be broken again. None of this is settled history. Almost all of it happened within a single human lifetime, and a meaningful chunk of it happened within the last 5 years alone. That's really the note worth ending on. This isn't a list of closed cases. It's a progress report, a snapshot of exactly how far our instruments, our math, and our patience have managed to push back the darkness so far. And every single line of it is subject to revision the moment someone builds a bigger telescope, waits a few more years for better data, or simply points an existing instrument somewhere nobody thought to look before. Every discovery covered in this video started the same way, as an anomaly, a number that didn't quite fit, a patch of sky that looked slightly wrong, a signal buried in noise that a careful researcher refused to write off as a fluke. That's really all any of this ever is. Patient people refusing to look away from something strange until it either explains itself or reveals something nobody expected. The universe was dark for hundreds of millions of years before the first star ever lit up. It's been dark, in one form or another, in nearly every direction we've ever looked since. And the honest, thrilling truth is that we've barely started mapping it.